Hello, I'm Chris Jackson. I'm an LLVM developer at Graphcore. I'm going to talk a little bit about SCEV-Based debuginfo salvaging in loop strength reduce, which is some work that's already in tree, and I recently upgraded with a couple of patches to extend the capabilities. The content of this talk builds on a couple of previous year's talks. They cover a lot of things in more detail than I'm going to, or I simplify a couple of things. So it's really worth having a look at those. In particular, the Scalar Evolution demystified was really helpful for me to understand Scalar Evolution. And part of this work was done whilst I was part of the Debug team at SN Systems in Bristol. And also an extra thanks to Stephen Tozer of that team, who his patch series for variadic location dbg.value intrinsics largely enabled this work. So I'll be covering just enough of loop strength reduce, or LSR, Scalar Evolution, or SCEV, and debuginfo intrinsics to understand the salvaging method. Each topic is worthy of several talks on its own. So the motivation, why attempt to salvage debuginfo with Scalar Evolution, LSR, what is gained and what is lost when running that pass that's relevant, Scalar Evolution, just the immediately relevant basics. Definitely check out the talk I mentioned earlier. Debuginfo intrinsics, again, we're going to look at debug.value very quickly, and then some details on the salvaging implementation. So loop strength reduce, as an optimization, substitutes operations with computationally cheaper ones. So for example, multiply for shift or for add. That creates opportunities for dead code elimination and copy propagation, eliminating variables and locations, and also rewrites induction variables to reduce operations inside the loop. So everyone can be happy about loop strength reduce all the time. Until, of course, we want to debug or step into some loops that have been optimized and run through LSR. And this can be difficult because sometimes the source induction variable can't be reproduced. It's been changed by LSR. And also the results of some operations are unavailable as some locations have been optimized out. And so if you step into a loop, and this has happened, that's a poor debugging experience, it's going to be hard to debug. And this was reflected by filing of issues. So quick look at Scalar Evolution. It's an analysis pass used by LSR, and also some other passes, but we won't cover their usage in this talk. And very simply, and the most important thing to understand, is that the analysis provides a means of reproducing the value for an expression per iteration of a loop. And we're going to look at a means of exploiting this analysis to recover debuginfo by recovering the value of locations that LSR has optimized out. SCEV expressions can be basic recurrences or chain recurrences. We're only concerned with the basic recurrence today. I'll explain in a little while later. So the form is shown at the bottom of a recurrence, at the bottom of the slide. So the start and the stride can refer to locations or to constants, and can also contain arithmetic, casts and logic operations. And so the start in a SCEV expression is the value of an expression when entering the loop. The stride describes the delta per loop iteration. So a very quick look at an example of LSR operating on a simple loop. So there's a pre and post LSR IR, and I've stripped down the IR a little bit for readability and just to demonstrate this example. And the source variable I maps to the SSA variable invars.iv. And you can see that after loop strength reduce, that has been optimized out. Invars.iv is no longer present. It's been replaced, or at least the IV in the loop has been replaced by a canonical IV from LSR. And also note the debug.value intrinsics, which I'll go into more detail in a second. Between the top and bottom IR, the location has now become undef. So why is that important? Debug.value is for reproducing the value only of a source variable. Its first argument is a single location or list of locations. The second is a reference to the source variable metadata, so the example is demonstrated on the slide. And the third is a dwarf expression, which I'll go into more detail shortly. The important thing about this intrinsic is that if any of the referred to locations in the first argument have become undef, then the debug.value no longer reproduces the source variable value or the value of the location. And so what that means is when debugging, you can't reproduce that source variable value. It's not available. It's missing. So there are more intrinsics for debuginfo. You can look at those in the talk I cited earlier, but we don't need to discuss those right now. So a dwarf expression, aside from being the third argument of a debug.value, describes an assembly program in the dwarf stack machine. It's expressed as a string of operations that refer to the first argument of the debug.value, which is one or more locations. And importantly, there are kind of two forms of debug.value. The first refers to a single location in the first operand, and that will generally result in quite terse dwarf expressions, but it's not that powerful. You can only reproduce values using computation that refers to a single location. The other form uses a list of locations as the first operand, and then those locations have to be referred to, and I've underlined them there, in the dwarf expression with dbg optimised-out args. So while you've got a more expressive, way more powerful and expressive form, it's also a lot more verbose potentially. So if you recall from the example, invars.iv mapped to the source variable I, which is also the source induction variable and something we'd be keen to have whilst debugging. We saw on the earlier slide that was optimized out and to some extent replaced by the LSR induction variable, lsr.iv. Now, don't have to worry about how exactly the SCEV expression that I have there is derived. It's only important to know that using SCEVs, we can derive the iteration count and then recover the value of a location. So the value is recovered using the iteration count expression. And so the example there, if we for invars.iv, if we know the start value, which is 5, and we know the stride value, the delta per iteration, then we can recover the value at any given iteration of the loop. But how to derive the iteration count? Well, we know that the LSR canonical induction variable will be present, and in this case, that's the SCEV expression. And so we're able to compute the iteration count by just reversing the SCEV, by inverting it. So we subtract the start value and then divide by the stride value, and we know which iteration count we're in. Okay, so motivation's clear. We want to be able to debug inside loops of optimized code, but LSR optimizes out some locations on which debuginfo is dependent. However, SCEV analysis provides expressions that allow us to reproduce the value of locations in terms of other locations and constants. And Dwarf provides a means of performing computations. So we'll combine all these together, use the Dwarf to recover the debuginfo, and we'll translate SCEV expressions into Dwarf expressions. So this is the kind of flow for SCEV-based salvaging. You'll see that it's in 2 stages. One either side of loop strength reduce. And what this has the effect of decoupling the salvaging from the optimization. And just as an observation, when I worked with a lot of debuginfo, I started to think that perhaps preservation of debuginfo should be something that optimization passes are obliged to preserve themselves. But this method demonstrates that there's an alternative, that's not always necessary if you have adequate analysis. So stage 1 takes place after scalar evolution analysis, and we'll just have a quick look. The first stage caches information on each debug.value in the loop body. If after LSR has run, these debug.value contain undef locations, then we'll try and use the salvaging methods to salvage these debug.value. So we also cache the locations referred to in the debug.value, the corresponding scalar evolution expression, and if one is present, a dwarf expression. Now, there are some limitations. Not all forms of SCEV can be translated to dwarf expression, or at least that hasn't been implemented for all forms of SCEV. So if a location with a SCEV that can't be translated is encountered, then it's not cached, and no salvaging will ever be attempted. So in the interim, loop strength reduction runs, and I discussed earlier some of the optimization effects, but it's important to consider the impact now specifically on debug.value arguments. Firstly, location references become undef. Not all locations. Some debug.value are given new expressions by loop strength reduction, and they still preserve debuginfo. However, some debug.value, they have the dwarf expression rewritten, but also some of their locations become undef. So we have intrinsics where debuginfo is lost, but the intrinsic has been modified by LSR. So we're kind of in an unknown state. It may not be possible to know exactly what LSR was trying to do in terms of salvaging operations. So finally, after LSR, is the actual salvaging step. For each debug.value that contains an undef location, or one or more undef locations, we'll try and restore the dwarf expression. This is necessary because, as I mentioned, LSR can sometimes modify the expression itself in an unsuccessful salvaging attempt. So the expression is restored to a last known good state, matching that pre-LSR, and we'll try and compute the values of the locations that have been optimized out that match that expression. And what we'll do is, so then for each missing location, we'll take the corresponding SCEV, translate it to a dwarf expression or sub-expression, and we'll also store the locations referred to by the SCEV and now the sub-expression, and the debug.value will be updated. So we merge the dwarf sub-expressions into the original expression and update the location argument, which will also entail removing those locations that were optimized out and are now undef, and adding the locations that have been added in the new dwarf expressions that were derived from the scalar evolution expressions. So a quick SCEV salvage example. So we'll see an example of a salvage expression, which is in the second box down, derived from an iteration count computation and the location scalar evolution expression. Remember from earlier, invars.iv was mapped to the source variable I, or the source induction variable, and was optimized out. So the first stage, I've split up the dwarf expression so you can perhaps see it a bit more clearly, is from lsr.iv, we subtract its start value, the constant 20, and then we divide by 4, which is the stride value. And that allows us to know which iteration count we're in. And then next, we're going to use the iteration count with the invars.iv, which has been optimized out scalar evolution expression. So we multiply by the stride value, and then we add the start value. And that enables us to recreate the value of the now missing invars.iv. But you'll note from the long expression at the top that the multiply by 1 has been omitted. And this is because there's logic inside SCEV salvage to recognize when a stack expression is just the identity function. And it would just be a kind of no-op, wasteful computationally and in terms of debug info size. So I mentioned earlier SCEV chain recurrences and said, well, I wasn't going to address those. So there's two reasons. Firstly, some instrumentation showed that debug.value that referred to locations with chain recurrent SCEVs were uncommon for LSR to optimize out. So there would have been a relatively low return on investment in implementing that. And also, in order to work out the value of a chain expression, it's necessary to compute binomial coefficients. And there's some nice code for that inside Scalar Evolution inside LLVM. But to write and maintain that and start outputting the Dwarf expression, I don't know. It would look like unreadable and quite difficult to maintain. It would be quite a lot of assembly. And so moving on to future work, obviously it would be really cool to implement like a binomial coefficient library in Dwarf, but as I said, that would be hard to maintain. So there's some ideas for some simple Dwarf expression tooling that would enable that. And also, if you ever get bored and have time to examine some of the expressions that are output by SCEV salvage, some of them are quite verbose and contain some what are effectively no-ops. You saw I tried to omit identity functions. Sometimes that doesn't occur. So that would be a good thing to work on. And while the expressions being output are correct, they have an impact on debuginfo size and also the complexity of the Dwarf expression that needs to be computed. Okay, thanks.
Are there any questions? No questions. Everybody's tired. Oh, yay. One question.
Hey, so you start out with an expression for computing some index in your loop.
Yes.
SCEV turns that into a much shorter expression, and then you invert SCEV and re-encode it as Dwarf, so you can get back to the original number.
Yeah, that's right. So for a location that's been optimized out, we've cached the SCEV for it. And if we know the iteration count, or what iteration count we're in, we can apply that to the SCEV to get the value. So take the start value and add the iteration count multiplied by the stride. But to do that, we need to know the iteration count, and yes, we just invert the SCEV for the induction variable, which must be present, or we wouldn't have a loop.
Okay, so it seems like it should be possible to compute the inverse of the SCEV at the same time that you're computing the original SCEV, and write that value directly into the debug value. So you don't have to produce this side cache of numbers that you then try to fish things back out of later.
That's an interesting idea. So invert the expression and write that into the debug.value to start with.
Yes, or just leave it as a SCEV value, which is only used by that debug value.
Leave it as a what, sorry?
Or leave it as just a standard variable, which is dead, except that it's referred to by the debug.value.
Oh, so as a variable outside of the intrinsic?
Yeah, and then do the encoding into Dwarf later. Sure,
I mean, that would be really cool to have things outside of the intrinsic. I hadn't really considered that. This was an attempt to compute as much as possible inside it, but that would certainly be handier. That would save a lot of work, definitely.
All right, that's all I've got.
Thank you.
Any other questions? Great, let's thank our speaker.
All right, thanks.